Hold a warm cup of coffee in a cool room and watch what happens over the next few minutes. The cup cools while the room warms, though you would barely notice the room changing. Energy flows from hot to cold until the temperatures equalize, and not a single joule disappears from existence. Yet, something has been lost that can never be recovered. What you just witnessed in that ordinary moment is the same process that will determine the ultimate fate of every star, every galaxy, and every structure in the observable universe. This is not a video about energy running out, because energy does not run out. The first law of thermodynamics guarantees that total energy in an isolated system remains constant, unchanging, eternal in the sense that you cannot create it from nothing and you cannot destroy it into nothing. Every joule that existed at the beginning of time still exists now and will exist forever. The problem is not that energy disappears, but that energy spreads out, diffuses, equilibrates, moving from concentrated and useful forms into dispersed and unusable forms. Hot coffee becomes lukewarm coffee in a slightly warmer room, and the difference that allowed work to be done, that powered the transfer, has been erased. This is the second law of thermodynamics, which describes something more unsettling than mere energy loss. It describes the slow and irreversible degradation of structure itself, not matter vanishing or energy disappearing, but the gradual erosion of all the differences, all the gradients, all the organized patterns that make complex processes possible. Stars shine because they are hot in a cold universe. Life exists because chemical gradients can be exploited to build and maintain order. Thought occurs because electrical potential differences flow through neural tissue. Every process you can name, every structure you can observe, every phenomenon you value exists because of differences, because something is hotter or more concentrated or higher in potential than something else. The second law tells us those differences erode over time in isolated systems where entropy does not decrease. Equilibrium approaches. Thermodynamically speaking, equilibrium means no gradients, no differences, no capacity for work, no structure in the meaningful sense. Energy is conserved, structure is not. By the end of this video, you will understand what entropy actually means in precise physical terms, why the second law is not a fundamental law in the same sense as energy conservation, but rather a statistical tendency of overwhelming probability. How the first and second laws work together rather than contradicting each other. What Boltzmann's revolutionary insight was and why it changed everything. And what physicists mean when they talk about the heat death of the universe. If you find value in explorations like this, in understanding the deep physical principles that shape everything from a cooling cup of coffee to the ultimate fate of the cosmos, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Starting with a phrase you have probably heard many times. Energy cannot be created or destroyed. This is the first law of thermodynamics, one of the most fundamental principles in physics. Total energy in an isolated system remains constant, changing form as heat becomes work and work becomes heat, as kinetic energy becomes potential energy, while the total amount never changes. Mathematically, this is often written as delta U equals Q minus W, where delta U represents the change in internal energy of a system. Q is heat added to the system, and W is work done by the system. Add heat and internal energy increases. Do work and internal energy decreases. The bookkeeping always balances. This law has not been violated anywhere we have ever looked, applying to engines and refrigerators, to stars and galaxies, to chemical reactions and nuclear processes. Energy conservation is so fundamental that when physicists encounter apparent violations, they assume they have missed some form of energy, rather than that conservation has failed. Here is the puzzle, though. If energy is conserved, if no energy ever vanishes, why does everything seem to run down? Hot things cool, batteries discharge, machines wear out. The past looks different from the future. Energy cannot be destroyed. The universe seems to be winding down anyway. The answer lies in a concept that is often misunderstood: entropy. Entropy is not chaos, despite what you may have heard, and it is not disorder in the everyday sense, not messiness or randomness in some vague qualitative way. In physics, entropy is a quantitative measure with a precise definition, and understanding that definition is key to understanding why everything evolves the way it does. The second law of thermodynamics states that for real processes, for irreversible processes, total entropy of an isolated system does not decrease. For an isolated system, delta S is greater than or equal to 0, and entropy can stay the same in idealized reversible processes. But in reality, it always increases. Rudolf Clausius coined the term entropy in 1865 and defined it through reversible heat transfer. ds equals delta Q reversible divided by T, meaning change in entropy equals heat transferred reversibly divided by absolute temperature. This gives entropy units of energy per temperature, joules per Kelvin. This thermodynamic definition tells you how to calculate entropy changes, though it does not tell you what entropy means at a fundamental level. That insight came later, from Ludwig Boltzmann. I remember when I first truly understood Boltzmann's idea, and I had to sit with it for a while because it changed everything I thought I knew about why time seems to have a direction. Boltzmann's revolutionary insight, developed through work in 1872, and especially a combinatorial argument presented in 1877, was that entropy is not some mysterious property of matter, but is about counting, about how many different microscopic arrangements, how many different ways of placing all the atoms and molecules are compatible with the same macroscopic state. Think about a deck of cards for a moment. 52 cards can be arranged in 52 factorial different orderings, which comes to approximately 8.066 times 10 to the 67th power arrangements, an almost incomprehensibly large number that far exceeds the number of atoms in the observable universe. Now ask yourself, how many of those arrangements are the specific, perfectly ordered arrangement where spades run ace to king, then hearts, then clubs, than diamonds? Exactly one. One arrangement out of 8.066 times 10 to the 67th. Shuffle a well-ordered deck randomly, and the probability that you will return to that exact ordered state is effectively zero. Not because some law prohibits it, not because shuffling destroys the order in some metaphysical sense, but simply because there is only one ordered arrangement and an astronomical number of disordered ones. This is the core of Boltzmann's insight. Macrostates with larger numbers of compatible microstates, what physicists call higher multiplicity, are overwhelmingly more probable. Systems evolve toward higher multiplicity states not because some force pushes them there, but because random microscopic interactions are statistically almost certain to land in a high multiplicity macrostate simply by chance. Entropy, in Boltzmann's statistical interpretation, is proportional to the logarithm of the number of microstates compatible with a given macrostate, where more microstates means higher entropy. The formula, often written as S proportional to the natural log of W, where W is the multiplicity, connects the abstract thermodynamic quantity to the concrete idea of counting arrangements. The Boltzmann constant, Kb, serves as the conversion factor between microscopic and macroscopic scales, approximately 1.380649 times 10 to the negative 23rd joules per Kelvin, or about 0.0000867173 electron volts per Kelvin. This number was fixed exactly in the 2019 redefinition of SI units and bridges the world of individual molecules to the world of thermometers and heat engines. Let me put this differently, with an analogy that has mathematical backbone. Consider a messy room. There are far more micro configurations that look messy than configurations that look tidy. So, if you randomly rearrange objects, you are almost certain to end up with something that looks messy. Not because randomness prefers mess, but because mess has astronomically more microstates than tidiness. Now consider ink dropped in water. Initially, the ink is concentrated in one spot, a low entropy and low multiplicity state. Diffusion spreads the ink until it distributes uniformly throughout the water, a high entropy and high multiplicity state. The first law holds throughout this process, since no energy vanishes, yet the initial structured distribution is lost. The ink molecules are still there, the water molecules are still there, total energy is the same, but the gradient, the concentration difference, has been erased. This is what the second law describes: the statistical tendency of systems to evolve toward macrostates with higher multiplicity. Not because energy disappears, but because high multiplicity states are overwhelmingly more probable than low multiplicity states. Let me take you through the history of how these ideas developed, because the story reveals something important about how scientific understanding builds on itself. 1824 brought Sadi Carnot, a French military engineer, analyzing the efficiency of heat engines. France had fallen behind Britain in industrial development, and Carnot wanted to understand the fundamental limits on engine efficiency. His approach was remarkably abstract, and rather than focusing on specific engine designs, he asked, what is the maximum amount of work that can be extracted from a given temperature difference? His analysis, using idealized cycles that bear his name, showed that efficiency depends only on the temperatures of hot and cold reservoirs, not on the working substance or the details of the engine. Carnot did not have the modern concepts of entropy or the second law, working instead within the caloric theory of heat, which treated heat as a conserved fluid. Despite this incorrect framework, his results about efficiency limits were correct, demonstrating that the mathematics did not depend on the underlying physical interpretation. He died young at 36 in a cholera epidemic, and his work was largely forgotten until rediscovered and extended by others, particularly Clausius and Thomson decades later. The 1840s brought James Prescott Joule, establishing the mechanical equivalence of heat through careful experiment. He measured how much mechanical work was needed to raise water temperature by a specific amount, and his paddle wheel experiment, where falling weights stirred water and heated it, became a classic demonstration. Joule showed that heat and mechanical work were interchangeable, that a specific amount of work always produced the same amount of heat regardless of how the conversion occurred. This was foundational evidence for energy conservation and the first law. Joule was a brewer by profession, his careful measurements reflecting both scientific curiosity and practical interest in efficiency. The unit of energy, the joule, is named in his honor. 1850 brought Rudolf Clausius, formulating an early version of the second law. Clausius recognized that heat does not spontaneously flow from cold to hot, that there is a directionality to thermal processes not captured by energy conservation alone. Over the following years, Clausius developed the formal concept of entropy as a state function, a quantity that depends only on the current state of a system, not on how it got there. 1852 brought William Thomson, later Lord Kelvin, publicly discussing what he called a universal tendency toward dissipation of mechanical energy. Thomson recognized that while energy is conserved, something else is not conserved: the capacity to do work, the differences and gradients that power processes. He saw this as a cosmic tendency, leading toward a far future where all energy has dissipated into uniform heat and no further processes can occur. This is historically connected to the later heat-death framing. 1865 brought Clausius coining the term entropy, derived from Greek words meaning transformation. He advanced entropy-based formulations of the second law, giving the field a precise vocabulary and mathematical framework. His statement of the second law was deceptively simple. Heat cannot spontaneously flow from a colder to a hotter body. This simple prohibition has profound consequences, implying the existence of entropy and the directionality of natural processes. 1872 and 1877 brought Ludwig Boltzmann, developing kinetic and statistical arguments that connected the second law to probability. In 1877, he presented the combinatorial argument, making the entropy-probability connection explicit. The insight that macrostates with more compatible microstates are statistically overwhelmingly more likely to occur. This was a revolutionary shift in understanding. Before Boltzmann, the second law seemed like a fundamental law of nature, a basic constraint on what processes are possible. After Boltzmann, the second law became a statistical tendency, not a fundamental prohibition, but an overwhelming probability. The second law does not say entropy cannot decrease, but says entropy almost certainly will not decrease in any macroscopic system, because the number of high entropy microstates is so vastly larger than the number of low entropy microstates that spontaneous entropy decrease is effectively impossible to observe. Think about that for a moment before we continue. The second law is not like conservation laws. Energy conservation, momentum conservation, charge conservation, these are exact and built into the structure of physics at the deepest level. The second law is different, statistical, emerging from counting, and probability rather than from fundamental symmetries. This distinction matters because it tells us something about the nature of irreversibility. Many microscopic laws of physics are time-symmetric, meaning the equations that govern individual particles look the same whether time runs forward or backward. Yet macroscopic processes have a clear direction. Hot coffee cools in a cool room and does not spontaneously heat up while the room cools down, even though energy conservation would be satisfied either way. Statistical mechanics explains this asymmetry. The reason hot coffee cools is not that some law prohibits heating, but that the macrostate, where coffee is hot and room is cool, has vastly fewer compatible microstates than the macrostate where both are lukewarm. Random thermal motion is almost certain to evolve the system toward the higher multiplicity state. Not because physics forbids the reverse, but because the reverse is statistically, astronomically unlikely. This is the part that still amazes me, even after years of thinking about it. The arrow of time. The reason the past looks different from the future. The reason memories point backward and causes precede effects. All of this connects to entropy and the statistical tendency of systems to evolve toward higher multiplicity macrostates. Let me explain what is actually lost when entropy increases, because this is where the distinction between energy and structure becomes clearest. Energy is not lost. What is lost is the capacity to do work, and the capacity to do work requires gradients, differences, imbalances. Consider a battery. A charged battery contains chemical energy stored in the arrangement of atoms and the potential for chemical reactions. And when you connect the battery to a circuit, current flows because there is a difference in chemical potential between the terminals. The battery does work, powering whatever device is connected. Eventually, the battery discharges. Energy is still present. The atoms are still there, but the chemical potential difference has been erased, and the battery has reached equilibrium. No more work can be extracted, not because energy has vanished, but because the gradient that allowed work to flow has been eliminated. This is what the second law describes at its core, the erosion of gradients. An analogy that helps is topography. Think of temperature differences and pressure differences as height differences, like hills and valleys in a landscape. Work comes from moving downhill, from flowing along gradients from high to low. And the second law says these gradients erode over time in closed systems. Hills flatten, valleys fill. The landscape becomes level. When the landscape is level, when there are no more height differences, no more downhills, the capacity for work is gone, even though all the matter and energy that made up the original landscape is still there. The stuff exists, the structure does not. Stars provide a cosmic example of this principle. A star functions as a long-lived gradient maintainer. Its core burns at millions or billions of degrees, while the space around it hovers cold, just a few degrees above absolute zero. This temperature difference, this gradient, is what allows the star to radiate energy, to shine, to power processes in the surrounding cosmos. The star maintains this gradient by fusing hydrogen into helium, releasing energy that keeps the core hot. As long as fuel remains, the gradient persists. The star fights equilibrium. When fuel runs out, though, the star cannot maintain its temperature difference and relaxes toward colder equilibrium, becoming a white dwarf, a neutron star, or a black hole, depending on its mass. Energy remains. The matter that made up the star still exists, but the gradient that allowed the star to shine has been eliminated. Structure has been lost. Across cosmological timescales, this process plays out everywhere. Stars exhaust their fuel, gradients erode, hot things cool, concentrated things spread. Everything evolves towards states of higher entropy, not because energy vanishes, but because high entropy states are overwhelmingly more probable. I want to pause here and make sure the distinction between the first and second laws is clear, because they are often confused or thought to contradict each other. The first law tells you how much energy exists. It is a conservation law, and energy cannot be created or destroyed, so the total amount is fixed. The second law tells you how usable that energy is. It is a statistical tendency, and energy spreads into more disordered and more probable configurations, so the capacity for work decreases. These do not contradict each other. The first law constrains the quantity of energy. The second law constrains the quality of energy, its availability for doing work. Both can be true simultaneously. Consider the warm cup cooling in a cool room. Energy flows from cup to room, but total energy is conserved, with the cup losing thermal energy and the room gaining it. First law satisfied. At the same time, entropy increases. Initially, there is a temperature difference, a gradient, a low entropy state with relatively few compatible microstates. Finally, there is no temperature difference, just equilibrium, a high entropy state with vastly more compatible microstates. Second law satisfied. No contradiction. The energy did not disappear, but spread out. The structure, the gradient, was lost, while the energy remained. This brings us to a question with profound implications. What happens when you apply this reasoning to the entire universe? Consider another example: mixing. Take two gases at the same temperature and pressure, but confined to separate halves of a container by a partition. Remove the partition and let them mix. No energy is exchanged since the gases are at the same temperature, so no heat flows. No work is done. Total energy stays exactly the same. Entropy increases, though, because there are vastly more ways to arrange two types of gas molecules throughout the whole container than to have them separated in halves. The mixing happens spontaneously because the mixed state has enormously higher multiplicity than the separated state. Once mixed, the gases do not spontaneously separate, not because some law forbids it, but because the probability of spontaneous separation is negligibly small. The system has found its equilibrium, the high entropy mixed state, and it stays there because there is no statistical tendency to leave. This is the entropy of mixing, and it has practical consequences. Separating mixed substances requires work, requires energy input, requires decreasing the entropy of the mixture while increasing it elsewhere. Distillation, filtration, reverse osmosis, all separation processes require energy, precisely because they are fighting the second law, decreasing local entropy by paying an entropy cost elsewhere. Consider the example of a heat engine. A heat engine operates between a hot reservoir and a cold reservoir. Heat flows from hot to cold, and some of that heat flow is converted to work. The engine does not violate the first law because the energy balance closes. Heat in equals work done plus heat out. It does not violate the second law because entropy increases overall even as work is extracted. Carnot, in 1824, worked out the theoretical maximum efficiency of such an engine. The Carnot efficiency depends only on the temperatures of the hot and cold reservoirs. Efficiency equals 1 minus T cold over T hot. The greater the temperature difference, the higher the possible efficiency. This has practical implications that affect everything from power plants to refrigerators. All devices that convert heat to work or work to cooling are constrained by thermodynamic efficiency limits. You cannot extract more work from a temperature difference than the Carnot limit allows. Entropy increase is the tax you pay for any real conversion process. Modern power plants approach Carnot efficiency as closely as engineering allows, but they cannot exceed it. The second law sets fundamental limits on what is achievable, limits that cannot be overcome by better engineering, only approached. Consider a gas expanding into a vacuum. Initially confined to half a container, the gas is released to fill the whole container, and its entropy increases. This happens because there are vastly more microstates where the gas molecules are spread throughout the whole container than microstates where they are confined to half. Random thermal motion will almost certainly land in a spread-out configuration. Energy is conserved throughout. The gas does no work against external pressure if the expansion is free. Temperature does not change. Total energy stays the same. What changes is the distribution. The gas goes from a concentrated, low-entropy state to a dispersed, high-entropy state. Structure is lost. Gradients are erased. The capacity for work that existed when the gas was compressed is eliminated. You could, in principle, compress the gas back to its original half of the container. This would require work, require energy input, require an external agent to fight against the statistical tendency. You would decrease the entropy of the gas, but you would increase the entropy of whatever provided the work, and the total entropy would increase. This is how the second law works in practice. Local entropy can decrease if you are willing to pay the cost in increased entropy elsewhere. Total entropy never decreases. Let me connect this to the everyday analogies I mentioned earlier. The messy room analogy captures the counting argument. There are more ways for a room to look messy than to look tidy, so random rearrangement tends toward mess. This is not because randomness prefers disorder in some metaphysical sense, but because mess has more microstates than tidiness. The ink in water analogy captures diffusion and gradient erasure. The ink spreads because the mixed state has vastly more microstates than the concentrated state. Energy is conserved, matter is conserved, but the structure, the concentration, is lost. The battery analogy captures the distinction between energy and usable energy. A discharged battery still contains energy, still has all its atoms, but the chemical potential gradient is gone. No more work can be extracted, even though energy remains. The topography analogy captures the erosion of gradients. Temperature and pressure differences are like height differences, and work comes from flowing downhill. The second law says the hills erode, the landscape flattens, the capacity for downhill flow decreases. All these analogies point to the same underlying physics. Systems evolve toward states of higher multiplicity, which means gradients smooth out and structure is lost while energy remains conserved. If entropy increases in closed systems, and if everything as a whole can be considered a closed system, then entropy should increase over time. Gradients should erode. Structure should degrade. Everything should evolve toward a state of maximum entropy. This is the concept of heat death, sometimes called the Big Freeze, and it represents one possible fate for the cosmos. Heat death does not mean everything becomes hot, despite what the term might suggest. It refers instead to a state where no thermal gradients remain, where everything has reached equilibrium, where energy still exists, but is so uniformly distributed that no work can be done. In such a state, there would be no stars, because star formation requires gravitational collapse of matter that is not uniformly distributed. There would be no processes driven by temperature differences, because there would be no temperature differences. There would be no complex structures, because complex structures require maintained gradients to persist. Energy would still exist, matter might still exist in some form, everything would be cold, dark, and approaching a state of maximum entropy, where nothing further could happen in the thermodynamic sense. William Thomson raised this possibility as early as 1852 in his discussion of the universal tendency toward dissipation of mechanical energy. The idea has been refined over the subsequent century and a half as understanding of both thermodynamics and cosmology has improved. The modern understanding of heat death is shaped by our knowledge of cosmic expansion. Everything is expanding. The Planck 2018 results, which provide a widely used baseline for cosmological parameters, give a Hubble constant of approximately 67.4 kilometers per second per megaparsec, or about 41.9 miles per second per megaparsec. This means galaxies are receding from each other, distances between cosmic structures are growing, and everything as a whole is becoming more dilute. Under the standard lambda CDM cosmological model, which includes a cosmological constant representing dark energy, this expansion continues and accelerates. Galaxies that are currently visible will eventually recede faster than light due to the expansion of space itself, crossing our cosmic horizon and becoming causally isolated forever. In this accelerating expansion scenario, the far future is increasingly cold and empty. Matter becomes more dilute as space expands. Temperature differences erode as systems equilibrate. The cosmic microwave background radiation, already a cold 2.7 Kelvin, continues to cool as its photons redshift. If dark energy remains constant, as a true cosmological constant would, this expansion continues forever, growing colder, emptier, more dilute, approaching a state of maximum entropy. There are ongoing investigations into whether dark energy might evolve with time. The DESI collaboration and other large-scale structure surveys continue to refine dark energy constraints. If dark energy is not constant, if it evolves or decays, the far future scenario could differ from the classic heat-death picture. As of now, though, observations are consistent with a cosmological constant, and the heat-death scenario remains the standard far future projection. Let me give you a sense of the timescales involved, because they are almost beyond comprehension. The current age of everything is about 13.8 billion years. Stars like our Sun live for about 10 billion years. The longest-lived stars, small red dwarfs, can burn for trillions of years. Conventional star formation is expected to end around 100 trillion years from now, about 10,000 times the current age of everything. We are in the very early cosmic morning by this measure, the first 1/100th of 1% of the time during which stars will exist. After conventional star formation ends, existing stars burn out over the following eras. The longest-lived red dwarfs continue for another 100 trillion years or so after star formation ceases, and then they too exhaust their fuel and fade. What remains after all the stars are gone? Stellar remnants. White dwarfs, the cores of dead sun-like stars, cool slowly toward absolute zero, with no internal energy source, gradually radiating away their heat over vast timescales. A white dwarf might take 10 to the 15th years or longer to cool to the point where it emits essentially no radiation, becoming a cold black dwarf. Neutron stars, the ultra-dense remnants of massive stars that exploded as supernovae, also cool slowly. They are born hot but have no fusion to sustain their temperature, cooling and fading over billions to trillions of years. Black holes, the remnants of the most massive stars, do not cool in the same way, containing no internal matter to radiate. Instead, through the quantum process of Hawking radiation, they very slowly evaporate, converting their mass to radiation over unimaginably long timescales. A stellar mass black hole, one with about 10 times the mass of the Sun, would take approximately 10 to the 67th years to evaporate completely, a 1 followed by 67 zeros. A timescale so long that even saying it is inconceivable understates how far it exceeds human experience or imagination. Supermassive black holes, the ones at the centers of galaxies with millions or billions of solar masses, take correspondingly longer. A black hole with a billion solar masses might take 10 to the 100th years to evaporate. Again, a number beyond comprehension. These timescales are relevant to the approach to maximum entropy. As everything ages past the stellar era, past the era of compact remnants, past the evaporation of black holes, it approaches the equilibrium state of heat death. I want to emphasize how far in the future these timescales are, though. The evaporation of black holes takes times that make the current age of everything, even the entire era of stars, look instantaneous by comparison. We are not at the end of cosmic history. We are at the very beginning. I want to address some nuances and common misconceptions, because the second law is often misunderstood in ways that lead to confusion. First nuance: order can locally increase without violating the second law. Crystals form, ice freezes from water, life builds complex structures from simpler components. Organisms maintain order against surrounding chaos. Civilizations construct buildings and write books and create art. None of this violates the second law because the second law applies to isolated systems, and living things and crystals and civilizations are not isolated systems but open systems that exchange energy and matter with their surroundings. When water freezes into ice, the entropy of the water decreases as water molecules become more ordered, more constrained, locked into a crystalline lattice. Taken alone, this would seem to violate the second law. What actually happens, though, is that freezing releases heat to the surroundings. The process of forming the ordered crystal produces thermal energy that increases the entropy of the environment. Total entropy, system plus environment, increases, even though local entropy decreases. This is how life works thermodynamically. Living organisms maintain internal order by increasing the entropy of their surroundings, consuming low-entropy food, and producing high-entropy waste heat. The total entropy budget balances, with increases in environmental entropy more than compensating for local decreases in organismal entropy. Humans building cities, creating art, writing books, all of this decreases local entropy in the sense that organized structures are being created. Yet it does not violate the second law because humans are not isolated systems. We consume energy, produce heat, increase the entropy of our surroundings in the process of maintaining and extending local order. The second law does not say entropy cannot decrease anywhere. It says entropy does not decrease for isolated systems. Open systems can and do decrease their local entropy by exporting entropy to their surroundings. Second nuance. The second law is statistical, not absolute. This is Boltzmann's key insight. Entropy increase is not a fundamental prohibition, but an overwhelming probability. Systems evolve toward higher entropy states because those states have vastly more compatible microstates, not because some force prevents low entropy states. In principle, entropy could decrease spontaneously. All the air molecules in a room could, by random thermal motion, happen to cluster in one corner, leaving a vacuum in the rest of the room. No law of physics forbids this. What makes it effectively impossible is probability. The number of microstates where air is evenly distributed is so astronomically larger than the number of microstates where air clusters in one corner that spontaneous clustering is never observed. Not because it cannot happen, but because the odds against it are beyond comprehension. Let me give you a sense of the numbers involved. 1 billion seconds is approximately 31.69 years, roughly half a human lifetime. This is a useful anchor for thinking about probability and time. If you shuffled a deck of cards once per second, how long would it take to see every possible arrangement? There are 52 factorial arrangements, about 8.066 times 10 to the 67th power. And at one shuffle per second, you would need about 2.5 times 10 to the 60 power years to see them all. A number so large it makes the current age of everything look like an eye blink. The probability of macroscopic, spontaneous entropy decrease is not just unlikely in the sense of winning the lottery, it is unlikely in the sense of something that would not be expected to happen once in the entire history of everything observable. Not once in a trillion similar systems, not once in any conceivable time frame. This is why the second law holds in practice, even though it is not fundamental in the same way energy conservation is fundamental. The statistics are so overwhelming that exceptions are not observed at macroscopic scales. Third nuance: microscopic fluctuations do occur. At very small scales, with very small numbers of particles, entropy can fluctuate. Individual molecules can move against the statistical flow. Small systems can temporarily decrease in entropy. This does not violate anything because the second law is a statement about macroscopic systems with large numbers of degrees of freedom. For small systems, fluctuations matter. For macroscopic systems, the law of large numbers takes over and fluctuations average out to produce the inexorable increase in entropy we observe. The second law is a limit of large numbers, an emergent behavior of systems with many particles, not a fundamental constraint on individual particles. Let me explore some specific examples in greater depth, because concrete illustrations help make abstract concepts tangible. Consider the process of ice melting. Ice is a highly ordered solid with water molecules locked into a crystalline lattice, each molecule in a fixed position relative to its neighbors. This is a low entropy state because there are relatively few ways to arrange molecules in the precise pattern of the crystal. When ice melts, molecules break free from the lattice and move freely as liquid. The number of possible arrangements increases enormously, since a liquid water molecule can be anywhere within the container, oriented in any direction. The multiplicity explodes and entropy increases. The energy to drive this transition comes from the surroundings as heat flows into the ice from the warmer environment, and the ice gains energy and uses it to break the bonds holding molecules in the lattice. Notice what happens to total entropy. The ice gains entropy as it melts, transitioning from ordered solid to disordered liquid, while the surroundings lose entropy because they lose heat at a certain temperature. The second law is satisfied because the entropy gain by the ice exceeds the entropy loss by the surroundings, as long as the melting occurs spontaneously at temperatures above the melting point. At exactly the melting temperature, the process is reversible, and entropy of ice plus surroundings remains constant. This is the borderline case, where the second law inequality becomes an equality. This example illustrates why phase transitions occur at specific temperatures. At low temperatures, the entropy cost of melting exceeds the entropy gain, so water stays frozen. At high temperatures, the entropy gain exceeds the cost, so ice melts. At the melting point exactly, the two balance. The same logic applies to boiling, sublimation, and other phase transitions. Each occurs at a temperature where the entropy economics shift from favoring one phase to favoring another. Let me give you another way to think about this transition. Water molecules in ice are not motionless, but vibrate in place within the crystal lattice. As you add heat, these vibrations become more energetic. At a certain point, the vibrations become strong enough to break the bonds holding molecules in their fixed positions, and the crystal structure collapses into the disordered liquid state. The melting point is the temperature at which the energetic cost of breaking bonds is exactly balanced by the entropic benefit of increased freedom of movement. Below that temperature, the energetic cost dominates and ice is stable. Above that temperature, the entropic benefit dominates and liquid water is stable. This same principle governs countless natural phenomena. Chemical reactions proceed in the direction that increases total entropy when you account for both the reacting system and its surroundings. Proteins fold into their functional shapes because the folded state maximizes total entropy when you include the water molecules that would otherwise be ordered around the unfolded protein. Crystals nucleate and grow because the crystalline arrangement increases total entropy even as it decreases local configurational entropy. The second law is not just a constraint on what can happen, it is a guide to what will happen, a predictor of the direction of spontaneous change. Consider the industrial implications of this principle. Every chemical process, every manufacturing operation, every energy conversion system operates within the constraints set by the second law. Chemical engineers designing reactors must account for entropy changes to predict whether reactions will proceed spontaneously. Mechanical engineers designing engines must accept that some fraction of input energy will inevitably be lost as waste heat. Electrical engineers designing power systems must plan for transmission losses that cannot be eliminated, only minimized. The second law sets hard limits. You cannot build a perpetual motion machine that does work indefinitely without energy input. You cannot build a heat engine more efficient than the Carnot limit. You cannot separate mixed substances without expending energy. These are not engineering challenges to be overcome with better technology. They are physical constraints built into the nature of reality. Understanding these constraints is the beginning of wisdom in engineering. Fighting against the second law is futile. Working within its constraints, finding creative ways to approach theoretical limits, designing systems that minimize entropy production while accomplishing useful work, this is where progress happens. The history of technology can be read as a history of increasingly efficient entropy management. Early steam engines converted less than 5% of the energy in coal to useful work. Modern combined cycle power plants approach 60% efficiency. This progress came not from violating the second law, but from better understanding how to work within its constraints. Similar progress has occurred in refrigeration, in chemical processing, in transportation. Each advance represents a better understanding of thermodynamics and a more sophisticated approach to managing energy flows and entropy production. The second law does not say efficiency cannot improve. It says efficiency has limits, and those limits are set by physics, not by human ingenuity. We can approach those limits more closely, but we cannot exceed them. Consider the example of life itself. Living organisms are highly ordered structures. Proteins fold into precise shapes. DNA stores information in specific sequences. Cells maintain internal environments strikingly different from their surroundings. All of this is low entropy relative to equilibrium. How does life maintain this order without violating the second law? By exporting entropy to the surroundings. Organisms consume low entropy food, molecules with concentrated chemical energy, and break down these molecules, extract useful work, and produce high entropy waste, heat, carbon dioxide, simpler molecules. Total entropy change, organism plus environment, is positive. The organism decreases its internal entropy or maintains it at a low level, but the entropy it exports exceeds this. Life is a local entropy minimum sustained by a flow of entropy to the surroundings. This is why life requires energy flow. Without input of low entropy energy, an organism cannot maintain its order against the statistical tendency toward equilibrium. Starve an organism of energy and it dies, its internal structures degrading toward higher entropy as the gradients that maintained them collapse. Photosynthesis captures low entropy sunlight, electromagnetic radiation with high energy photons, and uses it to build low entropy sugars from high entropy carbon dioxide and water. Cellular respiration releases the energy stored in those sugars, producing work and high entropy heat. The entire biosphere is a gradient-maintaining system, powered by the temperature difference between the hot sun and cold space. Earth intercepts a tiny fraction of the sun's output, uses it to drive complex processes, and radiates the energy back to space as low-temperature infrared. The entropy of the outgoing radiation exceeds the entropy of the incoming radiation, so the second law is satisfied, even as life maintains local order. This perspective reframes what life is thermodynamically, a self-sustaining, self-replicating process that maintains low entropy structure by coupling to energy flows that increase total entropy. Let me put the cosmic timescales in perspective with a familiar anchor. 1 billion seconds is approximately 31.69 years. This is roughly half a human lifetime. 1 trillion seconds, 10 to the 12th seconds, is about 31,690 years. This is longer than all of recorded human history. 1 quadrillion seconds, 10 to the 15th seconds, is about 31.69 million years. This is longer than the time since the extinction of the non-avian dinosaurs. 1 quintillion seconds, 10 to the 18th seconds, is about 31.69 billion years. This is more than twice the current age of everything observable. Now consider that the era of stars lasts about 3 times 10 to the 21 seconds. The evaporation time of stellar mass black holes is about 3 times 10 to the 74 seconds. The numbers quickly exceed any intuitive grasp. The second law operates on all these timescales. Entropy increases whether we are talking about a cup cooling in minutes, a star burning over billions of years, or a black hole evaporating over times that make billions of years look like an eye blink. The timescale does not change the physics. Entropy still tends to increase. Gradients still erode. Structure is still not conserved, even though energy is. The era of stars, from the formation of the first stars a few 100 million years after the cosmic beginning, to the burnout of the last red dwarfs 100 trillion years from now, represents a tiny fraction of the total time before heat death. Complex processes, structure, stars, potentially life, all of this exists in this early window. What comes after the stellar era is progressively colder, darker, more dilute. Gradients erode, structure degrades. The approach to maximum entropy continues, slowly, inexorably, over timescales that dwarf anything we can meaningfully imagine. Let me go deeper into some of the physical details, because understanding the mathematics helps clarify what the second law actually says. The first law, in one common form, states that delta U equals Q minus W. The change in internal energy of a system equals the heat added to the system minus the work done by the system. This is energy bookkeeping. Add heat, internal energy increases. Do work, internal energy decreases. The total always balances. The second law, in entropy terms, states that delta S is greater than or equal to 0 for an isolated system. Entropy change is non-negative. Equality holds only for idealized reversible processes. In reality, entropy increases. Clausius defined entropy through reversible heat transfer. ds equals delta Q reversible divided by T. This gives a way to calculate entropy changes for any process by imagining an equivalent reversible path between the same initial and final states. Boltzmann connected this macroscopic quantity to microscopic counting. Entropy is proportional to the logarithm of the number of microstates compatible with the macrostate. S proportional to K log W, where W is the multiplicity and K is the Boltzmann constant. The Boltzmann constant is approximately 1.380649 times 10 to the negative 23rd joules per Kelvin. This is the conversion factor between microscopic energies measured per molecule and macroscopic energies measured in bulk. It connects the world of atoms to the world of thermometers. The logarithm in Boltzmann's formula is important for several reasons. First, it makes entropy additive. If you have two independent systems with multiplicities W1 and W2, the combined system has multiplicity W1 times W2. The logarithm of a product is the sum of logarithms. So the entropy of the combined system is S1 plus S2. Entropy adds, which is what you want for an extensive quantity. Second, the logarithm tames the enormous numbers involved. A mole of gas has about 6.02 times 10 to the 23rd molecules. The number of microstates for such a system is beyond astronomical, but the logarithm brings it to a manageable scale. Think about the card shuffling example again. 52 factorial is about 8.066 times 10 to the 67th. The logarithm of this number is about 156. Entropy is proportional to the logarithm, so it grows only linearly, even when multiplicities grow exponentially. This logarithmic relationship means entropy increases relatively slowly even as the system explores its vast space of microstates. A factor of 10 increase in multiplicity only adds a constant to entropy. This is why entropy values in everyday units, joules per Kelvin, are not stupendously large numbers. The second law says this logarithm of microstates tends to increase. Systems evolve toward macrostates with higher multiplicity, not because physics forces them there, but because random microscopic dynamics are almost certain to end up in high multiplicity territory simply by chance. Let me explore what structure means in more concrete terms, because the abstraction can obscure the everyday relevance of these ideas. Your morning coffee has structure in the thermodynamic sense, because it is hot while the room is cool. That temperature difference is a gradient, an imbalance, a departure from equilibrium. As the coffee cools, that structure erodes. The gradient flattens. Energy spreads from the concentrated hotspot of the coffee into the diffuse thermal energy of the room. The toast you eat has structure, because the chemical bonds, carbohydrates, store energy in concentrated form. Your body breaks those bonds, releases the energy, and uses it to maintain your internal gradients, your body temperature, your iron concentrations, your pH levels. The waste products, carbon dioxide and water, have less chemical structure than the original carbohydrates. Energy has been conserved, but has spread into less useful forms. The car you drive has structure because the gasoline in its tank stores chemical energy at high density. Combustion releases that energy, does work on the pistons, and produces exhaust gases with less chemical structure than the original fuel. The car moves forward, but entropy has increased. Energy has spread out. The building you work in has structure because materials have been concentrated and arranged in specific patterns. Maintaining that structure requires ongoing energy input, heating and cooling systems fighting against temperature gradients, repairs fighting against material degradation, cleaning fighting against the tendency of ordered arrangements to become disordered. Every structure you can see, every system you depend on, every process you value exists because gradients are maintained against the second law's tendency toward equilibrium. The moment maintenance stops, degradation begins. This is not pessimistic, it is simply accurate. Understanding this helps clarify what we are actually doing when we build things, maintain things, or create order of any kind. We are fighting a statistical tendency, and we can only win locally and temporarily by paying an entropy cost elsewhere. The implications extend to information and computation. Information, in the physical sense, is also connected to entropy. A message has information content precisely because it is one specific arrangement out of many possible arrangements. A meaningful sentence is low entropy compared to a random string of letters, because there are far fewer meaningful sentences than random strings. Processing information, computing, storing data, all of these operations have thermodynamic costs. Erasing a bit of information, changing a memory cell from an unknown state to a known state, requires dissipating at least kT L⁻²2 joules of energy, where K is the Boltzmann constant and T is temperature. This is the Landauer limit, a fundamental connection between information and thermodynamics. Modern computers operate far above the Landauer limit, dissipating millions of times more energy per operation than theoretically necessary. This represents room for improvement, but the limit itself cannot be exceeded. Information processing requires energy expenditure and increases entropy, just like every other physical process. The computers you use, the phones in your pockets, the servers that power the internet, all of these are thermodynamic machines converting low-entropy electrical energy into high-entropy waste heat, while performing useful information processing in between. They are subject to the same constraints as heat engines and living organisms. This connection between information and thermodynamics has profound implications for questions about computation, intelligence, and even the nature of physics itself. Some physicists argue that information is fundamental, that the laws of physics are ultimately about information processing, and that entropy is the bridge connecting information theory to physical reality. These are deep waters, and the questions remain open. What matters for our purposes is recognizing that the second law touches everything, including the most abstract-seeming aspects of information and computation. Let me return to the title of this video. The energy is conserved, but the structure is not. What do I mean by structure in this context? Structure means maintained gradients. Structure means differences. Structure means temperature differences, pressure differences, density differences, chemical potential differences. Structure means the imbalances that allow work to be done and processes to occur. A star has structure because its core is hot and space is cold. And that temperature gradient is what allows the star to radiate, to shine, to power processes. A living organism has structure because it maintains chemical gradients pH differences, ion concentrations that differ from the surrounding environment. And those gradients are what allow metabolism, movement, thought. A battery has structure because it has separated charges, chemical potentials held in imbalance. And that imbalance is what allows current to flow when the circuit is connected. The second law says these structures erode in isolated systems. Gradients smooth out, differences disappear. Hot and cold mix to lukewarm. Concentrated and dilute mix to uniform. Energy remains through all of this. No joule is lost. The battery still contains atoms after it discharges. The star still has mass after it exhausts its fuel. The room still holds energy after the coffee cools. What is lost is the organization, the pattern, the difference that allowed processes to occur. This is what physicists mean when they talk about free energy. Not free as in costless, but free as in available for work. As entropy increases, free energy decreases. Energy becomes less available, less useful, less capable of driving processes. I want to pause here and think about what this means for complex systems and for us. Everything we value, everything we experience, everything we build exists because of maintained gradients. Stars shine because of temperature gradients. Life persists because of chemical gradients. Thought occurs because of electrical gradients. Civilization functions because of energy gradients, burning fuel to power machines, concentrating resources to build structures. The second law says all these gradients tend to erode in isolated systems. Over cosmic timescales, if we extrapolate current physics to the far future, the gradients we depend on will eventually be exhausted. This might sound bleak, but I want to frame it carefully. We are not isolated systems. Life maintains local order by exporting entropy. Civilizations can potentially extend their gradients, finding new energy sources, new ways to do work. The timescales involved are so vast, hundreds of trillions of years before star formation ends, that talking about the ultimate fate of the cosmos is very different from talking about any timescale relevant to human experience. What the second law offers is perspective. It tells us that structure requires maintenance. Gradients erode unless energy is expended to maintain them. Order is not free. Maintaining order against the statistical tendency toward equilibrium requires work. This is true at every scale. Your body maintains its temperature against the environment by metabolizing food. Your house maintains its temperature against the environment by heating or cooling. Stars maintain their temperature against space by fusing fuel. When the maintenance stops, equilibrium approaches. The fuel runs out. The gradients smooth. Structure is lost, while energy remains. Consider this thought experiment. Imagine two containers of water, one hot and one cold, separated by a conducting wall. Heat flows from hot to cold. The hot water cools, the cold water warms. Eventually, both reach the same intermediate temperature. No energy has been lost, and the total thermal energy of the two containers is exactly the same as when you started. First law satisfied. What has been lost is the gradient, the temperature difference that existed at the beginning, that could have been used to do work, to run a heat engine, to power a process. The capacity for work is gone, even though the energy remains. This is the essence of the second law. Not energy vanishing, but energy spreading out, evening out, becoming uniformly distributed and unavailable for work. Now scale this up to the cosmos. The cosmos contains vast temperature gradients. Stars burn at millions of degrees, while intergalactic space hovers just above absolute zero. Matter is concentrated in galaxies, galaxy clusters, and cosmic filaments, while voids between them contain almost nothing. These gradients, these concentrations and differences, are the structure of the cosmos. What allows stars to shine, galaxies to form, complex processes to occur. The second law says these gradients tend to erode over time. Stars burn their fuel and cool. Matter spreads out as space expands. Temperature differences diminish toward equilibrium. The timescales are vast. Conventional star formation continues for another 100 trillion years or so. Stellar remnants persist far longer. The ultimate approach to maximum entropy takes times that dwarf even these enormous numbers. The tendency is there, though, built into the statistics of how systems with many particles evolve. Everything trends toward higher entropy, toward smoother gradients, toward equilibrium. Let me address the question of irreversibility more carefully, because it touches on deep issues about the nature of time and physics. Consider what this means for the question of cosmic complexity. If entropy always increases, if structure always degrades, how did complex structures arise in the first place? How did stars form from diffuse gas? How did planets form from stellar debris? How did life emerge from non-living chemistry? The answer lies in understanding that the second law describes total entropy, not local entropy. Local entropy can decrease as long as total entropy increases by a larger amount. Stars form because gravitational collapse releases energy to the surroundings. A collapsing gas cloud becomes more ordered, its entropy decreasing as matter concentrates. At the same time, the gravitational potential energy released heats the surroundings, increasing their entropy by more than the decrease in the collapsing region. Total entropy increases even as local structure forms. This is counterintuitive at first. Gravity drives structure formation, and structure seems like order, like low entropy. The resolution is that gravitational systems have negative heat capacity. Adding energy makes them expand and cool, while removing energy makes them contract and heat up. This thermodynamic peculiarity means gravitational collapse increases entropy overall, even as it creates concentrated structures. The formation of stars, planets, and galaxies is not a violation of the second law, but a consequence of it, playing out in the strange thermodynamics of gravitationally bound systems. Life follows a similar pattern at a different scale. Living organisms are highly ordered locally, but they increase the entropy of their surroundings by a larger amount. A plant capturing sunlight and building glucose is creating local order while increasing total entropy by converting high-quality light into low-quality heat. An animal eating food and maintaining its body temperature is doing the same thing. The existence of complex structures, including living structures, is not evidence against the second law. It is evidence of how the second law operates in open systems that exchange energy with their surroundings. Local order can be purchased at the cost of increased disorder elsewhere. This has implications for the search for life elsewhere. If life requires energy flow to maintain its order, then we should expect life to arise where energy gradients exist and can be exploited. On Earth, the primary gradient is the temperature difference between the Sun and space. Life on Earth is powered by this gradient, either directly through photosynthesis or indirectly through food chains that ultimately trace back to photosynthesis. Other energy gradients could potentially support life. Chemical gradients in deep-sea hydrothermal vents support ecosystems independent of sunlight. Radioactive decay in planetary interiors provides energy that could potentially be exploited. Any persistent energy gradient is, in principle, a potential foundation for life. The second law does not tell us where life might exist, but it tells us what conditions life requires. Access to energy gradients that can be exploited to maintain local order against the statistical tendency toward equilibrium. This is a thermodynamic prerequisite for life as we understand it. Without energy flow, complex structures cannot persist. The search for life is in part a search for exploitable energy gradients in environments that permit complex chemistry. Many microscopic laws of physics are time-symmetric. The equations that govern how particles move and interact look the same whether time runs forward or backward. If you made a movie of atoms colliding and played it in reverse, the reversed movie would still obey the same physical laws. There is nothing in the fundamental equations that distinguishes past from future. Yet macroscopic processes have a clear direction. Hot coffee cools. Ice melts in a warm room. Mixed gases do not spontaneously separate. Memories point to the past, not the future. This directional behavior of macroscopic systems, the arrow of time, seems to conflict with the time symmetry of microscopic physics. Statistical mechanics resolves this apparent conflict. The key insight is that while microscopic dynamics are time symmetric, macroscopic behavior is not symmetric because of initial conditions and probability. Consider all the microstates compatible with a cup of hot coffee in a cool room. If you evolve these microstates forward in time using the microscopic laws, most of them evolve toward equilibrium, toward a state where the coffee and room are the same temperature. Now consider evolving those same microstates backward in time. Most of them also evolve toward equilibrium, toward states where temperature differences are smaller. This seems paradoxical. How can most microstates evolve toward equilibrium in both time directions? The resolution is that the initial state we start with is special. A hot cup in a cool room is a low entropy state with relatively few compatible microstates. If we start there and evolve forward, we move toward the vastly larger space of high entropy equilibrium states. If we had started in equilibrium and asked where those microstates came from in the past, we would find that most of them came from equilibrium in the past too. The arrow of time emerges because everything started in a low entropy state. Given a low entropy initial condition, evolution proceeds toward higher entropy in the future. This is the statistical arrow of time, explaining why macroscopic processes seem irreversible even though microscopic laws are reversible. The question of why everything started in a low entropy state is the past hypothesis problem. The second law explains why entropy increases given low initial entropy, but it does not explain the initial condition. This remains a deep and unsolved problem in cosmology and foundations of physics. Some physicists argue that low initial entropy is just a boundary condition, a contingent fact that does not require further explanation. Others seek dynamical explanations for why the early state was special. The question remains open. What we can say is that, given the initial conditions we observe, the second law correctly describes the evolution of entropy and the arrow of time. The asymmetry between past and future is not built into microscopic physics, but emerges from the combination of microscopic physics and special initial conditions. This has implications for how we understand causality and explanation. Causes precede effects because the direction of causality aligns with the direction of entropy increase. A cause is a low entropy state that constrains future evolution. An effect is the resulting high entropy state that follows from that constraint. Memories exist because forming a memory is an irreversible process that increases entropy. The brain state that constitutes a memory is correlated with a past event through a causal chain that involves entropy production. If entropy decreased with time, causes would follow effects. Memories would point to the future, and the entire structure of experience would be reversed. The direction of time as we experience it is intimately connected to the direction of entropy increase. This is not to say time is just entropy increase. Time is a more fundamental concept in physics, appearing in the equations of motion and the structure of space-time. The asymmetry of time, though, the fact that past and future are different, the arrow that points from before to after, is connected to thermodynamics and the second law. The second law touches on questions that go beyond physics into philosophy of time and philosophy of mind. Why does time seem to flow? Why can we remember the past but not the future? Why do causes precede effects? All of these questions connect to entropy and the statistical arrow. I find this perspective humbling. The fact that we can measure entropy, model stars, and project far future scenarios is a testament to human methods of understanding. Thermometers and statistics and telescopes bridge scales from atoms to galaxies. We can see the cooling cup in the morning kitchen and understand that the same processes, scaled up enormously, will shape the fate of stars and the far future of the cosmos. This bridging of scales, this ability to see patterns that repeat from the microscopic to the cosmological, is one of the great achievements of human inquiry. It does not require assigning meaning or intention to physical processes. It is simply understanding how things work, tracing causes and effects, counting microstates, and computing probabilities. Let me discuss what happens on cosmic timescales in more detail, because the scale of the numbers involved deserves careful attention. The current age of everything observable is approximately 13.8 billion years. In scientific notation, that is about 1.38 times 10 to the 10th power years. Our Sun is about 4.6 billion years old and has about another 5 billion years of hydrogen fusion remaining before it exhausts its core fuel and evolves off the main sequence. Stars like our Sun have total lifetimes of about 10 billion years. Smaller stars live longer. Red dwarf stars, the most common type in the galaxy, have masses so low that they fuse hydrogen slowly and can shine for trillions of years. A red dwarf with half the Sun's mass might shine for over 200 billion years, more than 15 times the current age of everything we can observe. The smallest red dwarfs, barely massive enough to sustain fusion, could shine for 10 trillion years or more. These stars will be the last to burn out in a cosmos where new star formation has ceased. Conventional star formation, the process by which gas clouds collapse to form new stars, depends on the availability of cold gas and gravitational instability. As space expands and ages, available gas is consumed by existing stars or ejected from galaxies. Eventually, around 100 trillion years from now, the conditions for new star formation will no longer be met. 100 trillion years is 10 to the 14th power years. That is roughly 10,000 times the current age of everything observable. We are in the very early cosmic morning by this measure, the first 1/100th of 1% of the time during which stars will exist. After star formation ends, existing stars burn out over the following eras. The longest-lived red dwarfs continue for another 100 trillion years or so after star formation ceases. Then they too exhaust their fuel and fade. What remains after all the stars are gone? Stellar remnants persist. White dwarfs, the cores of dead sun-like stars, cool slowly toward absolute zero. They have no internal energy source, so they gradually radiate away their heat over vast timescales. A white dwarf might take 10 to the 15th years or longer to cool to the point where it emits essentially no radiation, becoming a cold black dwarf. Neutron stars, the ultra-dense remnants of massive stars that exploded as supernovae, also cool slowly. They are born hot, but have no fusion to sustain their temperature. Over billions to trillions of years, they cool and fade. Black holes, the remnants of the most massive stars, do not cool in the same way. They contain no internal matter to radiate. Instead, quantum process of Hawking radiation, they very slowly evaporate, converting their mass to radiation over unimaginably long timescales. A stellar mass black hole, one with about 10 times the mass of the Sun, would take approximately 10 to the 67th years to evaporate completely. That is, a 1 followed by 67 zeros. It is a timescale so long that even saying it is inconceivable, understates how far it exceeds human experience or imagination. Supermassive black holes, The ones at the centers of galaxies with millions or billions of solar masses take correspondingly longer. A black hole with a billion solar masses might take 10 to the 100th years to evaporate. Again, a number beyond comprehension. These timescales are relevant to the approach to maximum entropy. As everything ages past the stellar era, past the era of compact remnants, past the evaporation of black holes, it approaches the equilibrium state of heat death. We are not at the end of cosmic history. We are at the very beginning. Let me reflect on the human dimension of these ideas, because thermodynamics is not just abstract physics, but connects to how we experience and navigate the world. Everything we do involves entropy change. Every thought, every movement, every process in our bodies increases total entropy, even as it maintains local order. When you think, neurons fire and ions flow across membranes and chemical reactions occur. Each of these processes increases entropy while maintaining the ordered structure of the brain. The entropy cost is paid by metabolizing food, converting low entropy chemical energy into high entropy heat. When you move, muscles contract and ATP is hydrolyzed and chemical potential is converted to mechanical work. Again, the process increases total entropy while accomplishing useful work. When you remember, the act of forming and retrieving memories involves irreversible processes. Memories exist because entropy increased during their formation, creating correlations between brain states and past events. We are thermodynamic beings, sustained by energy flows that maintain our order against the statistical tendency toward equilibrium. We exist because gradients can be exploited to do work, and we persist as long as we can maintain those internal gradients. This is not a metaphor, it is physics. The same equations that describe heat engines and cooling cups describe metabolism and thought. Consider what death means thermodynamically. Death is the failure to maintain internal gradients. When an organism dies, it can no longer exploit external energy to maintain its order. Equilibrium approaches. The structure breaks down. Entropy increases as the organized matter returns toward more probable, less ordered states. This is not a value judgment, it is a description. Death is the thermodynamic consequence of losing the ability to maintain gradients. Life fights against this tendency while it can. Every living organism is a local decrease in entropy sustained by a larger increase elsewhere. We eat to maintain ourselves. We breathe to power our metabolism. We maintain temperature, pH, ion concentrations, all the internal gradients that keep us functioning. The second law does not say life is impossible. It says life requires energy flow to maintain its order. Cut off the energy, and the order cannot persist. This perspective might seem cold or reductive. I do not experience it that way. Understanding the thermodynamics of life does not diminish its wonder. If anything, it deepens wonder. That complex, self-sustaining, self-replicating structures can emerge and persist against the statistical flow is remarkable. That we can understand this, can trace the energy flows and entropy budgets, can connect our existence to the fundamental physics is an achievement worth celebrating. We are not exempt from the second law. We are examples of it. Examples of how local order can be maintained while total entropy increases. Examples of the creative potential latent in thermodynamic constraints. Consider the broader picture of Earth as a system. Earth is not a closed system. It receives energy from the sun and radiates energy to space. This energy flow drives all the processes on Earth's surface, from weather to photosynthesis to the evolution of life. The sun provides high-quality energy, photons at high temperature with low entropy per unit energy. Earth radiates low-quality energy, infrared photons at low temperature with high entropy per unit energy. More entropy leaves Earth than arrives. The difference is what powers everything. Photosynthesis captures some of the incoming low-entropy sunlight and uses it to build low-entropy sugar molecules from high-entropy carbon dioxide and water. This chemical potential gradient then powers nearly all life on Earth, either directly in plants or indirectly in animals that eat plants. The entire biosphere functions as a gradient-maintaining system, a vast network of processes that maintain local order by coupling to the entropy flow from sun to space. Human civilization extends this pattern. We use concentrated energy sources, fossil fuels, nuclear fuels, renewable flows, to power machines, build structures, and maintain order against entropy. Our technology is thermodynamically similar to metabolism, exploiting gradients to do work. The energy we use is not destroyed, but converted, dispersed, and eventually radiated to space. The total energy budget of Earth closes. What we have is not infinite energy, but access to energy gradients, the difference between incoming sunlight and outgoing infrared, the chemical potential stored in fuels, the temperature differences we can exploit. When we worry about energy resources, we are not worried about energy disappearing, since energy is conserved. We are worried about running out of gradients, of concentrated, usable energy that can do work. The issue is not conservation, but availability, not the first law, but the second. This frames environmental and energy challenges in thermodynamic terms. The question is not whether energy exists, but whether we can access energy gradients sufficient to maintain the order we depend on. The second law sets limits on efficiency, on what is achievable, on how much work can be extracted from given gradients. Understanding thermodynamics does not solve these challenges, but it clarifies them. The constraints are physical, not just economic or political. The second law is not negotiable. Let me also address how this perspective connects to everyday experience in a more direct way. Every morning when you wake up, you are witnessing entropy in action. Your body maintained its temperature overnight by burning calories, converting the chemical energy of stored fat and glycogen into heat that dissipated into your blankets and the air. You wake up hungry because maintaining your internal gradients required fuel. The food you eat for breakfast is low-entropy matter, organized chemical energy stored in the bonds of carbohydrates, proteins, and fats. By the time that food leaves your body as carbon dioxide, water, and waste, the entropy will have increased substantially. The energy is not gone, but it has spread out, become less concentrated, become less available for work. When you take a shower, hot water flows from the shower head and cools as it contacts your body and the air. The temperature gradient between hot water and cool bathroom air is a form of structure, and that structure degrades as heat flows and temperatures equalize. The energy used to heat that water came from some source, natural gas or electricity, and ultimately traces back to a gradient somewhere. Chemical potential in fuel, nuclear potential in uranium, or the temperature difference between the sun and space for renewable sources. The electricity powering your home represents a maintained gradient, a voltage difference between the hot wire and neutral that allows current to flow and do work. That gradient is maintained by power plants, constantly converting some form of concentrated energy into electricity, while producing entropy as waste heat. The grid is a vast system for maintaining useful gradients against the second law's tendency to erase them. Your car, your appliances, your heating and cooling systems, your phone, your computer, all of these are devices for exploiting gradients to do useful work. Each one increases total entropy while providing local benefit. The entire infrastructure of modern civilization is an elaborate system for gradient management. When you come home tired at the end of the day, you are experiencing the cumulative effect of entropy production. Your body has burned fuel to power muscles and brain, producing heat and waste products, maintaining your internal order at the cost of increased disorder in your environment. The fatigue you feel is, in part, the thermodynamic cost of being an ordered system that does work. This is not meant to reduce human experience to thermodynamics. We are more than heat engines. Experience has meaning beyond energy accounting. What thermodynamics offers is a framework for understanding the physical substrate on which experience depends. We exist because gradients can be maintained. We persist because energy flows through us. We act because we can exploit differences between concentrated and dispersed energy. Understanding this does not diminish the value of experience. If anything, it highlights how remarkable it is that organized, experiencing beings exist at all in a cosmos trending toward equilibrium. We are local decreases in entropy, temporary islands of order in an ocean of increasing disorder. And the fact that we can understand this, can trace the physics of our own existence, is itself a triumph of organized complexity. These scientists built our understanding of thermodynamics through a combination of experiment, mathematical analysis, and conceptual innovation. They were working at the frontier of knowledge, often facing skepticism or opposition, gradually clarifying concepts that now seem obvious but were once controversial. The story of thermodynamics is a human story as much as a scientific one. Real people with their own motivations and struggles developed the ideas that now explain everything from cooling coffee to the far future of the cosmos. Boltzmann faced significant opposition to his ideas during his lifetime. The atomic hypothesis was not yet universally accepted, and the statistical interpretation of thermodynamics was controversial. Some physicists believed the laws of thermodynamics were fundamental and exact, not statistical and probabilistic. Boltzmann defended his work vigorously, engaging in extended debates with critics. The stress of these conflicts, combined with other factors, contributed to periods of depression. He died in 1906, shortly before his ideas became universally accepted with the confirmation of atomic theory. His tombstone in Vienna bears the equation S equals K log W, the formula connecting entropy to microstates. This equation is one of the most important in physics, bridging the macroscopic world of thermometers and heat engines to the microscopic world of atoms and probability. Thomson was a central figure in 19th century physics, contributing to electromagnetism, thermodynamics, and many practical applications. The absolute temperature scale, with 0 at absolute zero, is named the Kelvin scale in his honor. There is an important nuance I should address. In general relativity, global energy conservation for everything that exists and expands is subtle. The energy of photons redshifts as space expands. Their wavelength stretches, their frequency decreases, their energy per photon drops. Where does that energy go? In many cosmological spacetimes, there is no unique global conserved energy in the way there is for closed systems in Newtonian physics. This is a technical point that cosmologists debate carefully. The heat-death argument does not rely on perfect global energy conservation in the same way the first law works for a container of gas. It relies on local conservation laws, which do hold, and on the long-term behavior of matter and radiation in an expanding background. What matters for the heat-death picture is not that a specific energy total is conserved, but that gradients erode, that matter spreads out, that the conditions for maintaining complex processes become harder to sustain with cosmic aging. The current understanding of the far future is shaped by observations of dark energy and cosmic acceleration. Under the standard lambda-CDM model, the cosmological constant drives accelerated expansion. Galaxies recede from each other ever faster. Eventually, objects beyond a certain distance will be moving away faster than light can travel, crossing our cosmic horizon and becoming causally isolated forever. This accelerated expansion contributes to heat death by spreading matter out, by diluting the concentrations needed for structure formation, by cooling the cosmic microwave background radiation toward absolute zero. If dark energy remains constant, as a true cosmological constant would, this expansion continues forever. Everything becomes colder, emptier, more dilute, approaching a state of maximum entropy. There are ongoing investigations into whether dark energy might evolve with time. The DESI collaboration and other large-scale structure surveys continue to refine dark energy constraints. If dark energy is not constant, if it evolves or decays, the far future scenario could differ from the classic heat-death picture. As of now, though, observations are consistent with the cosmological constant, and the heat-death scenario remains the standard far future projection. What we can say with confidence is this: energy is conserved, structure is not. This contains a finite amount of usable energy, energy that can do work because it is concentrated or because gradients exist. As entropy increases, this usable energy decreases, not by disappearing, but by spreading out, by equilibrating, by losing the structure that made it useful. In the far future, under current projections, usable energy approaches zero, even though total energy remains constant. This is heat death, not energy vanishing, but energy becoming uniformly distributed and unavailable for work. The first law and the second law together describe this fate. Conservation holds throughout. Entropy increases throughout. The result is an approach to equilibrium, where structure has been lost, but energy remains. Let me also discuss the counterintuitive aspects of entropy more explicitly. Entropy is not disorder in the colloquial sense. Calling it disorder invites confusion, because disorder is a subjective judgment, while entropy is a quantitative measure. A crystal is more ordered than a liquid, and indeed has lower entropy. A gas of heavy atoms can have lower entropy than a gas of light atoms at the same temperature and pressure, even though both look equally disordered to the eye. Entropy is about counting microstates, not about appearance or aesthetic judgment. Entropy can decrease locally. Crystals form, ice freezes, life builds structure. These processes decrease local entropy while increasing total entropy by a larger amount. There is nothing mysterious about local entropy decrease when it is coupled to larger entropy increase elsewhere. Entropy is not a substance that flows. It is a state function, a property of the macroscopic state of a system. When we talk about entropy flow or entropy production, these are convenient descriptions of how entropy changes as systems interact, not claims about some material entity moving from place to place. The heat-death scenario is an extrapolation, not a certainty. It depends on current physical understanding, including the properties of dark energy continuing to hold indefinitely. New physics could change the picture. The timescales are so vast that many unknown factors could intervene. The second law is a tendency, not an absolute prohibition. In very small systems, fluctuations can decrease entropy. In principle, large fluctuations could occur in large systems with extraordinary improbability. What makes the second law effective is not logical necessity, but overwhelming statistical weight. These nuances do not undermine the second law. They clarify what it is, a statement about probability, about counting, about the statistical behavior of systems with many degrees of freedom. The heat-death picture is sometimes presented as bleak or nihilistic. I do not think it needs to be understood that way. Heat death is a physical constraint, a boundary condition for complexity. If gradients fade, long-lived complex processes become increasingly difficult. This is a fact about how physical systems evolve, not a narrative about meaning or purpose. What we do with that fact is up to us. The timescales involved are so vast that heat death is not a practical concern for any human planning horizon. Stars will shine for trillions of years. Complex processes can occur for durations that dwarf the current age of everything observable. The second law does not say complexity is impossible. It says complexity requires maintained gradients, requires energy expenditure, requires fighting against the statistical tendency toward equilibrium. Life does this. Civilizations can potentially do this at larger scales. The far future is not determined. dark energy might evolve. New physics might be discovered. The heat-death picture is based on extrapolating current physics to times so remote that any number of unknown factors could intervene. What the second law offers is not despair, but perspective. It tells us that structure is not free. Order requires maintenance. The gradients we depend on are finite resources that must be sustained or eventually exhausted. This seems to me a mature way to understand our situation. Remarkable complexity has emerged in a cosmos that trends toward equilibrium. And that complexity persists because gradients are maintained, because energy is expended, because work is done against the statistical flow. Let me also address a question that sometimes comes up. Does the second law apply to the entirety of existence? The second law, as typically stated, applies to isolated systems. Whether everything as a whole constitutes an isolated system in the relevant sense is a subtle question. In practical terms, the heat-death picture assumes that everything is effectively isolated, that there is no external energy source maintaining cosmic gradients. Under this assumption, entropy should increase over cosmic timescales and gradients should erode. There are technical issues with defining total entropy in general relativity. Cosmological horizons complicate the picture. Global energy conservation is subtle in expanding spacetimes. What physicists generally assume is that local thermodynamics works, that entropy increases in local systems, and that scaling this up to cosmological timescales leads to the heat-death picture as a limiting case. The details are more complex than for a gas in a box, but the basic tendency toward higher entropy is expected to hold. The alternative, that there is access to infinite free energy, or that some mechanism maintains gradients indefinitely, would require new physics beyond the standard model and beyond general relativity. Nothing in current observations suggests such mechanisms exist. This brings us back to the central theme. Energy is conserved, structure is not. There is a finite amount of usable energy, energy that can do work because it is concentrated or because gradients exist. As entropy increases, this usable energy decreases, not by disappearing, but by spreading out, by equilibrating, by losing the structure that made it useful. In the far future, under current projections, usable energy approaches zero, even though total energy remains constant. This is heat death. Not energy vanishing, but energy becoming uniformly distributed and unavailable for work. The first law and the second law together describe this fate. Conservation holds throughout. Entropy increases throughout. The result is an approach to equilibrium where structure has been lost, but energy remains. Boltzmann's leap was conceptual as much as mathematical. He took an abstract problem, why does time have a direction? Why do processes seem irreversible? And turned it into counting. How many microscopic arrangements correspond to what we see? The answer, when the counting is done, explains why macroscopic processes are effectively irreversible even when microscopic laws are time-symmetric. This is a triumph of physical reasoning, taking something mysterious and showing that it reduces to something you can count, that the apparent mystery dissolves when you track all the microstates. Boltzmann faced resistance to his ideas during his lifetime. The atomic hypothesis was not yet universally accepted. The statistical interpretation of thermodynamics was controversial. He defended his work vigorously, and history has vindicated him completely. Statistical mechanics is now foundational to physics, chemistry, and much of modern science. His tombstone in Vienna bears the equation S equals K log W, the connection between entropy and microstates, a formula that captures one of the deepest insights in physical science. When I first learned about Boltzmann's work, I had to put the book down and just sit with it for a while. The idea that something as fundamental as the arrow of time could emerge from counting, from pure probability and statistics, was startling. It changed how I thought about what explanation means in physics. Explanation does not always mean finding a deeper law. Sometimes it means showing that what seems like a law is actually an overwhelming statistical tendency. The second law is not like Newton's laws or Maxwell's equations, not a fundamental equation written into the structure of reality, but is what happens when you have many particles and track the probabilities. This statistical nature of the second law has implications. It means entropy increase is not absolute, and fluctuations occur at small scales. In principle, though never in practice at macroscopic scales, entropy could decrease spontaneously. It means the second law is emergent, arising from the collective behavior of many particles, not from some fundamental constraint on individual particles. It means the arrow of time is contingent in a sense, depending on the statistical behavior of macroscopic systems, not on time reversal asymmetry in fundamental physics. So, these are subtle points, but they matter for understanding what the second law really says. It is not a prohibition on certain processes, but a statement about overwhelming probability. Entropy increases because high entropy states are vastly more numerous than low entropy states, and random microscopic dynamics almost certainly lands in high entropy territory. Let me discuss the current status of research and what questions remain open. The basic framework of thermodynamics and statistical mechanics is well established. The first and second laws are not controversial. Boltzmann's statistical interpretation is standard physics. These are not cutting-edge hypotheses, but mature, thoroughly tested science. What remains active at the research frontier involves several directions. First, the role of entropy in cosmology continues to be explored. Black hole thermodynamics, which connects gravitational physics to entropy through the Bekenstein-Hawking entropy formula, raises profound questions about the nature of space and time. The entropy of black holes scales with surface area, not volume, suggesting deep connections between gravity, quantum mechanics, and information. Second, dark energy and the far future remain under investigation. The Planck 2018 results provide a baseline consistent with lambda CDM and a cosmological constant, though ongoing observations refine these constraints. The DESI collaboration and other surveys continue to probe dark energy's properties. If dark energy evolves with time rather than remaining constant, far future projections would need revision. Third, non-equilibrium thermodynamics and the thermodynamics of living systems are active areas. How do complex systems maintain order far from equilibrium? What are the fundamental limits on the efficiency of biological processes? These questions connect thermodynamics to biology and potentially to questions about life elsewhere. Fourth, the foundations of statistical mechanics continue to be examined. Why was the early state low entropy? This is the past hypothesis problem, the question of what set the initial conditions that gave entropy room to increase. The second law explains why entropy increases given low initial entropy, but it does not explain why initial entropy was low. This remains a deep and unsolved problem. The heat death picture is robust under current physics, though it depends on extrapolations over timescales so vast that many things could change. New physics might be discovered. Dark energy might behave differently than the cosmological constant predicts. Fundamental constants might vary. The standard picture is our best current projection, not a certainty. What we can say with confidence is the basic physics. The first law constrains energy totals. The second law describes the statistical tendency toward higher entropy, and this tendency shapes the evolution of everything from cooling cups to cooling stars. Let me bring this exploration to a close by returning to where we started. A warm cup cooling in a cool room. Heat flowing from hot to cold. Energy conserved, structure lost. The most ordinary of phenomena, repeated countless times every day, demonstrating the same physics that shapes the far future of the cosmos. The first law tells us energy cannot be created or destroyed. The total persists. Conservation holds. The second law tells us energy spreads out, equilibrates, loses its structure. Entropy increases, gradients erode. Together, they describe a situation where the quantity of energy remains constant, while the quality of energy, its availability for work, its organization into useful gradients, decreases over time. This is not a contradiction, but two complementary constraints. The first law tells you how much energy exists. The second law tells you how usable that energy is. Both can be true simultaneously, and both are true. Boltzmann showed us why the second law holds. It is about counting. Macrostates with more compatible microstates are overwhelmingly more probable, and systems evolve toward those higher multiplicity states not because some force pushes them there, but because random microscopic dynamics are almost certain to land there by chance. The arrow of time, the distinction between past and future, the reason memories point backward and not forward, connects to this statistical asymmetry. The past is different from the future because the past was lower entropy and the future will be higher entropy. We remember what happened because creating memories increases entropy, leaves traces, produces records. Stars shine because they maintain temperature gradients against cold space. life persists because organisms maintain chemical gradients against their surroundings. Everything we value and experience exists because gradients are maintained, because work is done, because energy is expended to fight the statistical tendency toward equilibrium. In the far future, under current physical understanding, those gradients will eventually erode. Star formation will cease around 100 trillion years from now. Stellar remnants will cool and fade. Everything will approach a state of maximum entropy, where energy still exists but is no longer available for work. This is heat death. Not energy vanishing, but structure vanishing. Not matter disappearing, but gradients disappearing. The end state is cold, dark, sparse, and approaching equilibrium. An approach that takes timescales so vast they make the current age of everything look like an eye blink. What do we make of this? I think the second law offers perspective rather than despair. It tells us that structure requires maintenance. Order is not free. The gradients we depend on are sustained through energy expenditure, and they are finite in a closed system. It also tells us that complexity is remarkable, that structure emerges at all, that gradients form and persist, that processes sustain themselves against the statistical current. This is worthy of wonder, not because it violates physics, but because physics allows for it. We find ourselves in a situation that permits complexity. Stars form, planets form, life emerges, intelligence develops, civilizations build. All of this is consistent with the second law, because local entropy can decrease while total entropy increases, because open systems can maintain order by exporting entropy to their surroundings. The far future is not our concern in any practical sense. 100 trillion years is a timescale beyond human comprehension, beyond any reasonable planning horizon. What matters for us is not heat death, but the here and now, the gradients we maintain, the structures we build, the order we sustain. The second law does not tell us life is futile, it tells us what the physical constraints are. Understanding those constraints is the beginning of wisdom, not the end of hope. The next time you hold a warm cup in a cool room and watch it cool, remember what you are seeing. Energy flowing from hot to cold, entropy increasing, structure eroding. The same physics that operates in your kitchen operates in the cores of stars and in the vastness between galaxies. The same statistical tendency that cools your coffee will, over cosmic timescales, approach the equilibrium of heat death. Energy is conserved, structure is not. This is what thermodynamics tells us. These are the laws that govern everything from atoms to galaxies, from moments to eons. Understanding them does not diminish wonder, it deepens it. Thank you for taking this journey with me through the first and second laws of thermodynamics, through Boltzmann's statistical insight, through the far future of the cosmos. These ideas deserve careful attention, and I appreciate you giving them that. If you found value in this exploration, consider subscribing to the channel. It helps these deep dives reach more curious minds. Sleep well tonight, and maybe think about the gradients that sustain you, the temperature differences and chemical potentials and energy flows that keep you alive and thinking. They are temporary, all gradients are, but they are here now, and they allow for everything you experience. Good night.